All right, so we are going to drive Kirchhoff equations under thermodynamics. So that this is opposite to physics, guys. So um yeah, it normally comes in an exam, so it's important that you pay attention, then it will both help. All right, so what we'll do is we need to know one thing first. Okay, without even wasting our time, shall we start? So driving Kirchhoff equations, what we need to know that this equation is just the relationship between the heat and the temperature change, all right, of these variables that we have. So it is just there to describe the relationship between temperature and heat. Okay, suppose I have the equation as follow. Okay, suppose I have the equation here. Let's say a plus b, then turning into c plus d. By the way, they are always coefficient, so here I'll put as a, here as b, then here as what, c, then here as d, like that. Okay, so this is the equation that we have. So we need to know that we said it's just the relationship of heat, which is the enthalpy, and change in temperature. So the temperature is going to be there. We will relate temperature to heat change. So what we need to know is that I said enthalpy, right? So the enthalpy of this is actually given as the product what is formed minus the reactant. All right, so say the change in enthalpy of this equation now, the change of the change in enthalpy of this equation will be presented as, so we'll say the change in enthalpy of this equation, it will be written as the summation of the product, enthalpy of product, all right, minus the summation of enthalpy of reactant, like that. Okay, so that's how we'll find it. So by this I'll say the entropy, all right, the entropy is given as, so I'll bring the product here. The product are these, light, so I'll say, I'll put just in the bracket like that. So I have c plus I have d, then d, open bracket, then minus the reactant. Now I have a plus b there. Okay, so what we are going to do here is so we are going to differentiate this one with respect to temperature. All right, so before that I'll write this as enthalpy change is equal to c, all right, then c plus again d, then minus a, all right, then b, b. All right, so what we need to do is enthalpy now, it will be given as, so we're going to differentiate this one, so master these steps, guys. So I'll differentiate this one with respect to temperature, because I said we are relating this heat to temperature. By the way, these are values of heat, so I want to relate to temperature. So what I'll do is I'll differentiate with respect to temperature. So what I'll say I'll do is I'll say um um I'll say uh enthalpy, all right, then differentiating with respect to, so I'm writing the same thing there, all right, then plus d, then minus a, just like that. These are my product, my reactant to say. Then I said I'm differentiating them with respect to temperature, so I'll say dt, everywhere dt. So I'm differentiating this one with respect to temperature. I said we are relating heat to temperature. That's about Kirchhoff. So from here, what I'm doing here is that, remember this enthalpy is the subject, right? So I need to distribute it also inside. So I was supposed to write enthalpy, all right, dt, then is equal to this constant again dt, all right. So I'm doing this everywhere. Okay, so that's So this is dH, all right, then dt, then C plus again C, again dt, dH, the enthalpy, then dt, then minus again this coefficient, then dH, which is the enthalpy, then dt, which is the temperature, then the change in temperature. So we are relating the change of heat over the change of temperature, the change of heat over the change of temperature, just like that. Again, just like that. Then we'll have B there. Okay, so from here we can see now that we have something here of which we need to know that there was change. So when you see that there's the enthalpy, all right, over temperature like that, this is equal to Cp, all right. We remember this identity. Again, when we have change in internal energy over dt, this is equal to Cv. Okay, so away from this, our interest now is based on our interest now is based on Cp, right? So we can see now that we have change in enthalpy over temperature that will give us what? Cp, right? So remember here, everything here is a change, right? We are trying to differentiate, to subtract product minus what? Minus reactant. So all these are what? Cp, Cp, Cp. So what I'm going to do here is, I was saying this is change, right? This is change. So I'll say this is Cp. So I'll say this is change in Cp, all right? Then is equal to, again here there is Cp. So I'll say C, which is the number of moles, then Cp there, all right, C again plus this is supposed to be D there, all right, this is supposed to be D, then here again D, all right. So here there was also supposed to be A. I've made a mistake. So then what I'll do here again, I'll say D, it's again Cp, so I'll say D, then Cp, D there. So again minus, I have A, Cp, then A, all right, minus again here, when change we have enthalpy over temperature, then that's the Cp. So we said now this is B, then Cp, B, like that. Okay, so we can see that this is just a change. These are number of moles which are changing, the rest are the constant. So we'll say there's change in mole, all right. So these moles were changing. Okay, so I'll say enthalpy now, all right. I'm just letting to say, the meaning is that enthalpy that we had there, all right, over temperature there is equal to the change in what? In Cp. Remember these are number of moles which we are changing, so we can say C plus D, then minus A plus C, B. That's a change we have there. So what I'll do here, I'll say, so mark this one. So since there's change in moles, I'll say now dH over dt is equal to, there is change in mole, all right. So I'll say change in mole, then Cp is constant because Cp was constant to everything. So therefore I'm saying change in enthalpy over temperature, over change in temperature, this will be, there was change in number of moles, then Cp, like that. Okay, so meaning that change in enthalpy, which is heat, is equal to change in the number of moles, then Cp, then this I can multiply throughout the times dt. Okay, so I can multiply times the dt. Okay, so this dt will go under the dt, so here we'll have dt like that, meaning that enthalpy change will be given by change in number of moles, all right, then Cp, which is constant pressure, then dt, like that. Okay, similarly, if I have now in terms of volume, So I'll say, I mean in terms of volume, yes, I'll say change in internal energy is equal to change in number of moles, then CV, then dt. So these are what we call Kirchoff's equations. So you can also write them as, like for this one you can write it as change in enthalpy is equal to change in number of moles, then Cp, then there's change in temperature, like that. Again, for internal energy you can write it as change in number of moles, then Cp, then change in what? Temperature, like that. Okay, so that's how you can write. So now that if the temperature was now like large, very big, so we can modify this equation by doing this. Suppose now you are now, so you'll be writing equation 1, equation 2 when you are answering the exam questions. All right, so now what we'll do here is suppose the temperature was such a big number. All right, the change in temperature was big, meaning that the entropy or just the heat capacity Cp will be constant, will be independent. So what we'll do is, if the temperature is big, okay, I can modify this equation by saying, I can relate to say change in Cp, all right, change in Cp here that I have with temperature. So I'll say, I can relate to say change in Cp, which is now capacity, all right, will be given by the change of this expression. I'll say, I'll put gamma there, then again I'll put beta there, all right. Temperature, I'm trying to put it independent of the what, of the entropy, so I mean of the heat capacity. So then here it will be temperature 2. So this is how temperature will be big, because it's changing from small to big. So now we are trying just to modify this equation, otherwise these are what you call Kirchoff's equations. Then from there, what we'll do here, we'll say, since we noticed that there was change in this one, okay, there was change in this one when it was related to enthalpy. So what I'll do here, I'll say delta, or just let me not say delta, so I'll say change in enthalpy is equal to the same thing here, all right, then plus gamma T2, like that. So now that we are now, what I'll do is we are going to integrate this equation with respect to what, to t. So how do we integrate this one? So we'll say dh, all right, is equal to, so we integrate this a, all right, plus again we integrate this beta that we have, plus again we integrate this gamma we have there. Okay, so how do we do this then? Integrating this one, so whenever you integrate, let's say dt, all right, integral of dt, this will be t, just like here the integral of enthalpy, that will be just enthalpy. I'll put just change here, all right, because that was change. I'll put change there like that, but it's supposed to be just h. So then from here, integrating this one, it's more like it is a constant, like integrating 2, that will be 2x, right? So here it will be also 80. Okay, so what I'll do is I'll say integrating this one, now it will be I'll add 1 there on top there, right? Now I don't have 1 there on top, so what I'll do is I don't have the variable, so I'll just write it as there will be change of this guy, which is the gamma, all right. So now I'll attach the temperature, all right, with the power 1. So I have temperature 2 minus temperature 1, like that. Hope that is clear. I'm just trying to modify this equation and try to master it. So I'm just modifying this equation, all right. So the issue is just modifying the equation. So from there, then I'm also modifying at t. Remember, now we have t here, so integrating this one, I'll add there, that will be 2, right? So that power 2, I won't really show it as 2. I'll just say now you divide throughout what you have done on top, so it will be 2, right? So I'll divide throughout by 2, I mean that will be like this. Then I'll put the same gamma there, all right. Then there was change. By the way, you put change in gamma like that, then temperature 2, all right, minus temperature is temperature 2 at this point. So we have temperature 1, then temperature 1 like that. So you say the change now is like that. Then these are raised to the power 2 because that was what has happened after integrating, right? So from there, then what I'll do is I'll say plus again. So here when we put 1 there, that would be 3, right? So that would be 1 over 3. Then change in what? In gamma, all right? Then open bracket, we have temperature 2 minus temperature 1. So now these ones are raised now to the power 3 because they have the power 3 like that. So this is now the equation that is integrated Kirchoff's law, wow, modified. So it was supposed to end here, but we have modified it further using gamma, beta, alpha to this point. So this is the integrated Kirchoff's law or Kirchoff's equation. So you need to show this in an exam for you to get, I don't know, your marks that will be given. So this is what you need to do. Alright, so that is it about Kirchoff's law. You just need to master all these steps, how heat is now changing with the temperature. So that's about Kirchoff's. Okay. Alright, so that is it about Kirchoff's. That's how you'll be deriving Kirchoff's equation.